Jai Hind everyone. This is Dr. Naresh Kumar from Akgec Engineering College, Ghaziabad. Welcome to the class of Communication Engineering. So, in this lecture, we will cover the topic Introduction to Frequency Modulation, that is a kind of angle modulation. So, let's start the lecture. So, basically, frequency modulation is a type of angle modulation. In the previous lecture, we have studied that what is modulation and what is the need of modulation. Basically, in the communication system, the message signal cannot be transmitted directly. It is transmitted with the help of a high frequency carrier signal. We use high frequency along with the message signal, and the characteristics of the carrier signal are varied according to the message signal. This process is basically known as the modulation, and this is the one of the most important process that is being used in the transmitter side. We have studied the modulation is required because to reduce the antenna size or to ensure the practicality of the antenna. Moreover, the modulation is also required to avoid the intermixing, for using the multiplexing, and for achieving the long distance communication are the other benefits that we get with the help of modulation. So, in the modulation, the characteristics of carrier signal are varied. So, the characteristics that are the mainly which can be varied according to the message signal are maybe amplitude, frequency and phase. So, in the previous lecture we have studied that when the amplitude of the carrier is varied according to message signal, this is known as the amplitude modulation. Now, when the frequency of the carrier signal is varied according to the message signal, this type of modulation scheme is known as the frequency modulation. And when the phase of the carrier is changed according to message signal, this is called as the phase modulation or PM. Now, these two type of modulations are combinedly covered under the term angle modulation. Okay. So, in the angle modulation, the frequency or phase of the carrier is varied according to the message signal. Because let us say we have a carrier signal Ct equal to Vc cos of omega Ct plus phi c. So, this is a carrier signal where this omega c is 2 pi fc, where this fc is carrier frequency, whereas this phi c denotes the phase. So, basically the factor inside this bracket is basically cos of some angle. So, this may be represented by theta. So, let us say this is angle. So, basically whenever we will vary the frequency fc or whenever we will vary the phase phi c, basically we are varying the angle theta according to the message signal. That is why this type of modulation scheme is known as the angle modulation. So, that is the reason for using the term angle modulation. So, in the frequency modulation, the frequency this fc will be changed according to message signal, and in the phase modulation this phi c will be changed according to message signal. Now, let us have the mathematical expression for the phase modulation and frequency modulation. So, in the previous slide we have shown this is the, let us say the carrier signal is here in terms of E, we are writing the Ec cos of omega Ct plus phi c. This is the carrier. So, according to the phase modulation, this angle phi c is changed according to the message signal. So, the equation for the PM can be written as Ec cos of omega Ct plus Kp into xt. Okay, where this kp is the phase sensitivity, and this xt is the message signal. So basically we are changing the phase of the carrier signal according to message signal. So this may be written as the equation for the phase modulation. So in this case we have the carrier signal where this phase of the carrier is changed according to the message signal xt. In the similar way, in the case of frequency modulation, where we have the frequency of the carrier signal is changed according to the message signal. So whenever the frequency changes, we get different values of frequency, or we can say that different instantaneous values of the frequency. So here let's say in the frequency modulation, the instantaneous value of the frequency fi can be obtained by changing the carrier frequency. So carrier frequency may be increased or decreased. So we can have fi equal to fc plus minus kf into xt, where this again kf is frequency sensitivity factor, that how much there is variation in the frequency with the change in the instantaneous value of the magnitude of the message signal, that is volt. So that's why the unit for this may be written as the KFC, where this KF is frequency sensitivity and unit is hertz per volt. So in this way we can get the instantaneous value of the frequency. Now we have studied amplitude modulation. What are the advantages, disadvantages or application of the angle modulation, so that we can prefer this over the amplitude modulation, or that's why we are studying the amplitude angle modulation. So the main advantage, disadvantage and applications of angle modulation can be summarized as: the advantages of the angle modulation are reduction in the noise, improved system fidelity, and more efficient use of power. So these are the three advantages that we get using the angle modulation over the amplitude modulation. In the similar way, there are some disadvantages also, such as increased bandwidth. For example, bandwidth of FM is more as compared to the AM. Then more complex circuits. The circuitry available for example, let's say on the receiver side is complex in the case of FM as compared to AM. So the complex circuitry is used. The main applications of the angle modulation may be in the case of radio broadcasting, TV sound transmission, two-way mobile radio, cellular radio, microwave communication and satellite communication, etc. So in these application areas we can prefer or use the angle modulation over the amplitude modulation. So now as we have studied, the angle modulation has two types, FM and then we have PM, phase modulation and frequency modulation. So as clear from the name, frequency modulation is where the frequency of the carrier signal varies according to the amplitude of the modulating signal, and amplitude remains constant. Only the frequency varies according to the message signal and amplitude remains constant, that's the frequency modulation. And in the FM, we vary the frequency as we have studied. The instantaneous value of frequency will be carrier frequency plus minus, that is frequency sensitivity factor into message signal. So the instantaneous value of the frequency varies. So this variation in frequency can be denoted in terms of the frequency deviation. This frequency deviation can be noted either as delta f or maybe through delta f. Now let's see the waveform for the frequency modulation signal. This is the message signal or modulating signal. Then we have a high frequency carrier signal. Okay, so let's say this is the carrier. Now the frequency of this carrier signal is varied according to the message signal. So this modulated signal or FM modulated signal is here. This is the FM modulated signal. In this case, we can see that the frequency of the carrier signal is fixed. Here the FC is fixed, that is not changing. But in the frequency modulation, the frequency of the carrier will change according to the message signal. So here we have, when the amplitude of the message signal is increasing, we can say that the frequency in the starting of the carrier is remaining constant, but when the magnitude starts increasing, the frequency of the carrier signal will also start increasing. Here the magnitude maximum, so here the frequency will be maximum. So we can get a maximum frequency point here. Now from this point onwards, the magnitude keep on decreasing, so the frequency also keep on decreasing. At this point we have magnitude as minimum, so at this point we will have the minimum frequency. And again then start increasing, then the frequency also starts increasing. So there is a variation in the frequency of the carrier signal which can be clearly observed here. For more clear understanding, another waveform is again represented. This is a modulating or message signal. As the magnitude is increasing, the frequency is increasing. Here we are getting the maximum frequency corresponding to the maximum amplitude of the message signal. So again there is decrease in the magnitude, and at this point we have the minimum frequency corresponding to the minimum magnitude, and in between the frequency keep on decreasing. And after this point magnitude again start increasing, so frequency again starts increasing, and at this point we will have the again high frequency. So the change in the frequency is clearly visible here. Then basically this is the comparison of AM and FM modulated waveforms. As we have studied, in the case of AM, amplitude of the carrier varies. In the case of FM, frequency of the carrier signal varies. So that can be seen in this diagram, where we have, this is the message signal, this is a carrier signal, high frequency sinusoidal carrier signal. Then we have this FM waveform, where clearly we can see that the points of high frequency, and then we have points corresponding to low frequency also. Then again frequency is high, then again frequency is low. And we can see that in the case of FM, the amplitude is constant throughout. Amplitude is constant. Whereas in the case of AM, we can clearly see that the frequency of the waveform is constant. where the magnitude of the carrier signal from this point onwards, the magnitude of the carrier signal is changing. So at this point we have the maximum magnitude, so it is V max, and at this instant of time we have the minimum magnitude, so we have the V minimum. So the magnitude of the amplitude, so the carrier signal is varied according to the message signal. Then let's have some derivation for the equation of frequency modulation. Let's take a sinusoidal carrier message signal and carrier signal. First of all, we have a message signal, that is Vm equal to small v, Vm equal to Vm sine of omega mt plus phi m. Then we take a sinusoidal carrier signal where this Vc equal to Vc sine of omega ct plus phi c. So this is the message, this is the carrier, and as we have studied, this is the type of angle modulation. Frequency modulation is type of angle modulation. So basically here we will have the angle theta. So we can write this as Vc sine of theta. So basically whenever there is a change in the frequency according to Fm, basically we are changing the theta. So variation in this theta is to be calculated in terms of omega. So basically in the Fm we have to calculate theta in terms of omega, because whenever there is change in omega, theta angle will change. So basically this can be represented here like this: at t equal to 0, whenever there is a change in the omega, there will be change in the angle theta. So we will compute the theta in terms of omega for computing the derivation for the frequency modulation. This will be at t equal to up to f. So by definition, we have the frequency of the carrier signal is changed according to the message. So instantaneous value of frequency fi equal to fc plus kf into message signal. This is message signal. So we are changing the frequency or getting the instantaneous value of frequency by varying this carrier frequency with this factor kf, which is frequency sensitivity, and into the message signal. According to message signal, we are changing the frequency value. So for getting this maximum deviation, this sin theta must be equal to 1, so that we can have the maximum variation. So this, whenever this sine, we will have sine of 90 degree to have this value 1. So this becomes fc plus minus kf into Vm, where this value kf into Vm indicates the variation in the frequency of carrier signal as per the amplitude of this message signal. So this basically shows the frequency variation. So this may be termed as the frequency deviation delta f, or may be denoted as delta f. So this term we have delta f equal to kf into Vm. This delta f is basically nothing but the deviation. This is frequency deviation. Then this we have already studied. Then in terms of omega, we can have instantaneous value of frequency of the carrier signal changed with value from omega c with this factor. Again, this is for omega we are using 2 pi, and otherwise we will have in the last equation we will have kf into message signal. So message signal is Vm sine of omega mt. So this is the value of omega, new value of changed value of omega. As we have studied, we have to compute the value of this theta in terms of variation in the omega. So this value of theta can be obtained by integrating the omega. We can get the value of this theta, and that value we can put in the equation Vc cos of theta or Vc into sine of theta, as we have put it earlier. So putting the equation, we can get theta in terms of omega by integrating the value of this omega as we have done previously. So by integrating this, we can have omega t, omega ct, and then we have 2 pi kf Vm cos of omega m t by omega m. This omega m can be represented as 2 pi fm. This 2 pi can cut with this 2 pi, and we know that this kf into Vm is denoted as the frequency deviation delta f. So we can write as this theta equal to omega ct plus delta f over fm cos of omega m t, where this factor, now delta f by fm factor, this is most important, denoted by the mf, known as the modulation index in the case of frequency modulation. So this is the mf, most important, is known as the modulation index. Modulation index in the case of fm, which gives the depth or measure of the extent of modulation that we are performing, that is extent up to which we are changing the frequency of the carrier signal according to message signal. So we have theta equal to omega ct plus mf cos of omega m t. So this value of theta can be put in the earlier equation that we have studied in the starting. So putting that value in the equation, we have Vfm equal to Vc sine, this was the value of theta. So putting this value of theta, we get the equation for the frequency modulation. So this is the standard equation that can be used for the representation of frequency modulation. Basically, there can be relation between the phase modulation and frequency modulation. Let's go to the previous slide. In this slide, we have seen that this equation can be again represented as, by integrating omega c, we get omega ct plus, now this factor can be represented as like this, integral of 2 pi kf, this factor Vm sine omega t, this can be represented as the message signal xt dt. This is the message signal. Okay, and where this factor 2 pi kf is constant, so we can take this out as out of the integral. So this equation may be written as omega ct plus 2 pi kf integral xt dt. Okay, so the equation of fm can be represented in this integral form. So basically we can have the relation between the frequency modulation and phase modulation. So the equation for the fm, as we have discussed previously, can be written as, this equation can be written as modulated signal st equal to, we have, so let's say in terms of ec, we can write as ec cos of theta, where theta, as we have discussed previously, can be written as EC cos of 2 pi FCT, that is omega CT, plus 2 pi kf into integral 0 to t over time xt into dt. Okay. So this is the equation for corresponding to the FM. So this is the equation corresponding to the FM, and corresponding to PM we can also write the equation. Phase modulation can be written as in the similar way, EC cos of 2 pi FCT plus Kp into xt. Okay. So compare these two equations. If we can have 2 pi kf equal to Kp, then these two equations can be compared. The only difference is here we have the xt, where in this case we have the integral of xt. So this gives an important comparison or relation between this is the phase modulation and this is the frequency modulation. The main important is here is the relation between the two is we can get this phase modulation from the frequency modulation if we use the d by dt. That is, for the frequency modulator at the input side with the x message signal, if we can apply a differentiator, then we get the PM from the FM. In the similar way, if we have a phase modulator, then at the input of the message signal, if we apply an integrator, we can get the phase modulation. So this important relation defines that we can get or generate the phase modulation from the FM or FM from the phase modulator. So this is shown here in the diagram, that is generation of FM from the phase modulator. So we have a phase modulator and where the message signal is applied through an integrator to a phase modulator. Then the output will be the FM wave, and vice versa. If we have a frequency modulator and at the input of the message signal, if we apply a differentiator, then output will be the phase modulation. That is through the relation that we have obtained previously. So in this way we can generate the FM from the PM and PM from the FM modulation technique. So again, this is the relation shown through the equations, that is expression for the phase modulation from the frequency modulation. So there is a relation between the two and we can generate phase modulation from FM and vice versa. So this is the reference book that I have used for this lecture. Thank you everyone. Jai Hind.